right. Got it. Okay. Okay. All right. We can start. Welcome to CS176P, Programmable Networks. I know this is not how we want this quarter to start, but here we are, still handling and dealing pandemic. So today's lecture is basically intro, and we're going to just understand what this course is about. Maybe give you a better perspective of whether this is the right course for you or not. But I'll try to give you a sense of what exactly are the set of topics that we're going to cover, what you should expect, and what I want you to learn from this course. So let's, before we start talking about the content, let's talk about people here. So my name is Arpit, and I'm an assistant professor here at UCSP. This is kind of like my second, third year, I would say, at UCSP. I joined here in 2019, and as you can imagine, almost all my tenure here has been during the pandemic. So I was very excited to finally teach a class in person, but that was not supposed to happen, at least for now. For 2 weeks, it doesn't seem like that's going to happen, and I'm keeping my fingers crossed. Hopefully we all get to see each other in person soon. We have 2 teaching assistants for this course. Both of them are graduate students working with me right now. So Rohan Bhatia, he's I would say lead TA, because he helped prepare multiple programming assignments for this course last year as well. And we have a new PhD student, Punal Smail Khan. He will also be TAing for this course. And you'll be meeting these 2 TAs for the office hours, as well as the discussion section that we have every Friday. So, the first thing that I will recommend you all is to, skim through the website, try to familiarize yourself with, what to expect in the course in terms of syllabus, timings. I have posted tentative dates for when exactly the programming assignments or the quizzes will be released. There might be a few, changes here and there, which I will update on the website. But, overall, the schedule will look something like what I have posted online. So, there is also information about the office hour timings for both Rohan and Punal, as well as the discussion section. All right, so what are the key goals for this class, right? So I have the title for this course is Programmable Networks. The official title is something else, but I've been trying to change it. So, it takes time at UCSB to change the course title. But, conventionally, this course was taught focusing more on, socket programming and stuff for networking. But, in my opinion, that's a bit dated set of things to teach. What is more, current and trendy right now is to learn about software-defined networking. For good or bad reasons, there are very few schools out there who specifically teach students about software-defined networking. It's kind of like, usually covered in passing. But since we have 3 set of courses specifically focused on networking, that gives us a unique opportunity to dig deeper into specific topics. And software-defined networking, as trendy as it sounds, it is very, very relevant and has been transformational in enabling all these big cloud content providers, service providers to do what they're doing right now, right? So this explosion of content that you see around you, a lot of that credit goes to software-defined networking. And in this class, we will try to understand why and how, right? But before we do that, I think the basic things that I want you to learn from this class is to just understand what software-defined networking really means, right? And what are the basic definitions, building blocks when we talk about software-defined networking. In the process, we will try to understand that, why was it required in the first place? What was the motivation behind software-defined networking? How it evolved over time, right? So all these good ideas, nobody comes up with the best idea at the first go. So there is a lot of iteration in how these engineering concepts evolve over time. So we will also traverse the journey of how these ideas came up, what motivated each of those ideas, and then how people, group together or map together different concepts to, have a more unified understanding of what software-defined networking is. And then what, more importantly, we'll try to understand, how exactly we can, apply these concepts in practice, right? So there will be a lot of hands-on experience as part of this course, which I'll talk soon. like talking about skills, as I was mentioning, that we will learn a new programming language, which is called P4, which is used to program hardware switches in networking, right? And I think you might feel that like I just learned Python and I just learned C, and now I have to learn one more language. I think if you have learned C or C++, even Python, you have some basic sense of how programming languages are, right? And I think you understand some basic concepts like primitives and functions and all those things. So I think that background will be very relevant for us to understand what P4 is. But I would say P4 is very interesting and exciting language to learn and master. It does not have the best abstraction, I would say, but it does enable us to control or configure the outline of a hardware switch, right? And that's very powerful. And we will see why that is powerful. And we will also learn how we can, like develop new applications for network devices, right? And that's going to be very powerful, because if we can run, like, what we will learn will be basic applications, but once you know how to build these basic applications, you can just, the possibilities are endless, and you can think about all new applications that you can write on your own. And something that I want to bring up here, when we talk about software-defined networking, when we talk about programmable networks, is that I was looking at the feedback that some of you gave about 176A, and some of you were, like, it's an exciting course, but you were kind of like concerned that there were a lot of protocols to learn about and keep track of. And I think, some good news about software-defined networking is that you don't really have to know a lot of protocols, learn or mug about a lot of protocols. You can create your own protocols, right? So when I refer to this hardware switch as PISA switch, the PISA here actually stands for protocol independent switch architecture. So the switch architecture is independent of what protocols you want to run on top of it, right? And that's kind of like coming through the flexibility that it supports. You can write your own protocol and make it work with these new generation programmable switches, right? And that's what we're going to learn. That's very powerful and empowering. We'll see how, and we'll also see like how exactly we can leverage that power and program these switches, program these devices, and develop new applications for networking, and how others have developed applications and learn from their experiences as well. As part of this, I think so we will learn P4, but what we will also learn is like the nuances of the software stack of a modern software-defined networking stack. What does that software stack looks like? What are its components? And we will use a state-of-the-art SDN controller and write an application on top of it, right? So I think you will understand how that workflow works. And at the end of this course, you will feel confident about knowing intelligently about what software-defined networking really means. And you'll feel confident that, like if some new requirement comes in terms of a new application use case, you'll feel confident that you can write or develop those applications on your own. And I think like, if that is the state where we reach at the end of this course, at the end of this quarter, I think that will be success for us, right? Moving on, the workload in evaluation is focused around quizzes and programming assignments and midterm and term exams. So we will have around a total of 6 quizzes over the quarter, which will weigh for 30% of your, like grades. And then we have 3 programming assignments, but I would call it like 4 because 1 is ungraded, but that's kind of like, just to get you started, set up the VM, understand what type of dev environment you'll be working and operating on. So, but that's ungraded, but that's kind of like required for doing any of the 3 assignments, right? So I think that's why I'm, like calling it 3+1, and that will total the 40% of the evaluation that we have for the course. And finally, we'll have midterm and interim exams for this course. Both quizzes and midterm and terms will focus more on what is explicitly covered in the lecture as well as the discussion section, right? So, discussion section and lecture will complement each other. We'll learn the high-level concepts here, and then we'll dig a bit deeper into how these things are really applied in practice in the discussion section. So they are kind of like complementary to each other. And overall, I think like participating in discussion section and understanding the nuances of programming these P4 programs or writing P4 programs will help you, be prepared for the programming assignments, right? So I will highly encourage you to actively participate in the discussion sections, which will be led by the 2 teaching assistants that I mentioned earlier. That will be a great, exciting and learning opportunity for you all. So talking a bit about the lectures, I want these lectures to be in person, but We are not in control here. The lectures will cover three broad categories. One will be focused more on the building blocks of SDN, like what really constitutes and makes an SDN. And then we will focus on the applications of SDN, like from principle, like very fundamental approach of like what is why exactly SDN was developed, motivations, like the key fundamental use cases that drove SDN, how they're leveraging those principles developed in SDN, like making things work. We'll focus more on wide area networks or data center networks, and try to understand how software-defined networking helped Google or Amazon or Microsoft to scale up their network when it comes to a wide area network, which is the global WAN, which is spread across multiple continents. How were they using these software-defined networking to manage those complex networks and make them more cost-effective? And also how they were managing or using software-defined networking to simplify management of their data center networks, and make the best use of limited resources that they had, relatively limited resources that they had, right? So we'll learn about those applications. And at the tail end part of this course, we will learn about the future directions. We'll learn about the recent trends that came up, new set of applications that are out there. And even though there has been a lot of work in this space, I would say this is still like an open area, and there is a scope of a lot more innovations to come in this space. And I'll give you a sense of how things, or how the different building blocks and applications that we have learned so far are kind of like base for the new generation of research and new generation of ideas and products coming out in this space. So that's the exposure that we will be covering as we move forward in this course. Talking about the references and books. So, this like I was mentioning earlier that, very few universities teach software-defined networking. And one big reason is that it is still an evolving area, right? So typically you learn concepts that have been established for 10 years at least, and then it becomes kind of like, more organized in terms of ideas, and structure is like, better structure is out there. So it gets easier to teach them. This is an evolving area. I think, you ask the top researchers, they're still grappling with how do we answer different fundamental questions, especially from teaching perspective. But that doesn't mean that we should not learn that, right? So like, so what we are, rather than using or referring to a conventional textbook, we'll be following this online textbook. It's called SDN, a systems approach. And the systems approach series has been written by Larry Peterson and his collaborators. So Larry Peterson was a faculty at Princeton, then he moved to Arizona, but he was also part of this Open Networking Foundation and multiple other organizations that basically materialized or like translated all these ideas in the academia to practice. And he was kind of like the front face for all these activities. And it's a delight to read his book. But also he takes into consideration that like we need to focus more on the systems approach here rather than just mugging the protocols and all these things, right? So I find that book very interesting and exciting, but at the same time, it's a bit thin in terms of details, right? So, like I'll complement that with more research papers. I'll complement that with, more articles that we can read. And I like for most of the lectures, I have a reading list of papers and articles that you can read. But I want to mention that, like you don't have to read them for quizzes or the end term exams, right? That's not my expectation. It is for your own knowledge. I am using them as a reference to, crystallize all these lecture notes for you. But if you want, you should. And, like if you have, like challenges reading those research papers or articles, you're more than welcome to come to me during the office hours, and I'll be more than happy to, guide you through how to read them. But, that's not really the objective, right? So, and this is different from how this course was offered last year, because last year students were expected to write reviews of the research papers that we were covering. But I've tried to, like tame that down a bit, because for undergrad students, it's a bit difficult to read research papers and make sense out of it. So, it will be my job to crystallize all that knowledge into lectures for you, simplify things for you. But at the same time, those references are out there. I will highly encourage you if you're curious to read those things, but if not, then don't worry too much about it. About the quizzes, so as you can see on the course website, the links to the quizzes will be available on the respective dates. Like most of the links are probably not working right now because like they will be released in a chronological order. But what you should expect from these quizzes is that like the key concepts that we have covered in the lectures but also some of the topics and problems that we have covered in the discussion section, right? So you have to put your attention on both these things, and we'll do our job to make sure that lectures and discussion section are self-contained and you have everything that you need. I don't think we will ask you any questions that we didn't cover in the lecture, we didn't discuss in the lecture or the discussion section. But if something comes up, then we can we will provide you enough support to answer the question that we will be discussing in the quizzes, right? So it will not be very difficult, but I think as long as you pay attention to the lectures and discussion sections, then you should be able to answer most of the questions here. About the programming assignments, I mentioned earlier that there will be 3 main programming assignments and 1 ungraded assignment. So ungraded assignment will be released very soon. And there you're just going to set up the environment as a virtual machine. And then the assignment 1 will be focusing on setting up a topology. So you learn something about a tool called Mininet. And this is a tool that networking practitioners and researchers use heavily to emulate networks in a in a local environment, right? So I can actually create a network topology on my laptop and then run experiments on it, and reproduce them, basically publish them as a program, and then others can reproduce that on their own machines and laptops. So this is a very powerful tool that was developed late 2000, and we will be learning about that, and it has been actively used in the community. And so that's one part. The second part will be that we'll be learning how to write a P4 program such that from these hardware switches we can collect some state or features from the network traffic that is underlying there, right? And then the second assignment will be focusing more on passive measurement or passive monitoring of queue sizes. We'll learn something about these runtime interfaces between the controller and the network and these hardware devices. And then we also want to learn how we can use this information to control or manage congestion in the network, right? And then finally, the assignment 3 will be focusing on, this will be a bit more hands-on experience for you to learn how you can write a new software-defined networking application for the ONOS controller. So ONOS controller is one of the, there are multiple controllers that are used in industry right now. ONOS is one which is kind of gaining a lot of traction in the community for reasons that it is open sourced and it is actively maintained. Right, so there are a lot of open sourced controller SDN controllers out there, but they're not very actively maintained. And then there are a lot of vendor specific controllers, but then by definition they're vendor specific, so not everybody's interested in that, right? So ONOS is kind of like a sweet spot. We will learn about the basics and principles of ONOS, the motivation behind it, the story behind it, and we will also learn how it works. And then eventually, by the time it comes to assignment 3 time, you'll be prepared to write a software-defined networking application on top of it, right? So I think that's kind of like the cherry on the cake here. That once you are done with assignment 3, you'll feel very confident that if somebody gives you a task for writing a new SDN app, you can actually write that on a state-of-the-art SDN controller. That will be very powerful and empowering. So we have been talking about software-defined networking a lot, and now I'm going to dive a bit more into the details here. But before I do that, let me give you folks an opportunity to ask some questions. So if you have any questions so far about the logistics that I was talking about, feel free to ask me on that. I can take a small pause here. Feel free to unmute yourself if you have questions. And I see some questions already posted before. So one question is, are the quizzes online? So yes, the quizzes will be online, and we'll be releasing, you can expect a Google Form style quizzes. And we'll be releasing that on the course website at the appropriate date, listed on the course website. Yes, so there will be time. The quizzes, like the question is are the quizzes timed? Yes, so there will be time. There is a deadline set. I have marked the deadline on the course website already. As I said, there might be some minor adjustments to those dates given some conflicts and concerns coming from you folks. But other than that, we have those dates in place. Typically, a quiz should take maybe half an hour to finish, maybe 1 hour at max. Depending on how thorough you are with the lectures, but if you know the answer, it should not take you more than 15 minutes, right? But if you have to refer to the lectures and go back, then maybe an hour, but that's about it. So one question is, will we be allowed to partner for programming assignments? The answer is no. The programming assignments have to be done individually. So that's not a team effort. And I think it will be good for you to, do those programming assignments on your own. That said, I think, we'll have an active discussions, going on Slack. We'll have a Slack channel for each of those assignments, and some obvious questions you can ask here. But I think from delivery perspective, each of you have to do it on your own. More questions? All right, so I think maybe this is a good time to move on. Before I start giving my own perspective about software-defined networking, I want to hear from you folks. Have you heard about software-defined networking before? And other than the reference to this course, or me talking about it a few minutes ago, did you hear about software-defined networking? What is your understanding of that? Anybody wants to take a jab at that? Okay, so 176A briefly covered what software-defined networking is. So can anybody try to summarize it for me? What is your understanding? Okay, we have some answers, right? So, dynamic software as opposed to hardware for routing. I don't know how to parse that, but it's approximately correct, and we'll learn how. And then there is some comment about Google using it. Oh yeah, Google uses it. Almost all big enterprises use it, right? So in one way or the other, right? Maybe it's not the exact same thing that Google uses, but Google uses one of the most, I would say one of the most advanced version of software-defined networking, but different companies have some version of software-defined networking running, operating their networks. Any other comment about software-defined networking? All right. So somebody mentions about, rather than programming the hardware for routing and forwarding, it is basically trying to express, if my reading is correct, it is basically trying to express the logic for forwarding or routing as a program, rather than having this hard coding of hardware device. You write a control program, and then some magic makes it work, right? And that's kind of in line with what software-defined networking is, but we need to be more precise, and that's something that we will, I would want you to have a very clear takeaway that you go out and somebody asks you, so what is software-defined networking? That is a question that you should know answer for sure, right? And it's not very difficult. It is very intuitive, and it's a very natural and organic thing that happened in networking, because this type of software-defined something was happening everywhere, and it was just a matter of time that it happened for networking. But I think unlike other areas and disciplines, networking is much harder to do or to enable software-defined networking. So we'll learn those challenges, why, how, but let's try to understand the basics here. So when we say software-defined networking, there are a couple of requirements. One is that there is a separation between the control plane, that is the plane that is controlling the network, and the data plane, the plane which is carrying the traffic, right? So when we think about any network device, the device, think about a router, right? So you took 176A, what router is. A packet comes into a router, it looks into forwarding information base or FIB and figures out that, okay, what is the next hop that it has to go? Then there are some changes made to the packet's header, and then packet is sent out to that egress port, right? So basically this is the data plane, right? So this is where the packet is handled by the network device. Now the question is that what is the logic that decides the entries into the forwarding information base of that router, right? So who decides that what are the forwarding entries in a particular device, right? So that is where there is a difference between the traditional networking view and software-defined networking. So when we think about traditional network view, what happens is that there is a software running on those devices itself. And that software is basically, like running a control protocol. Think of BGP, which you probably heard of, or Ospf. These are routing protocols that you probably have heard of in 176A. So all these routing protocols, these routers have a software program that is running on it. Then it is trying to send some messages around and try to figure out the state of the network, right? So it is trying to figure out who's its neighbor, what is the routing path to a destination, and then based on that, it updates the entries locally on its device, right? So this is something which you can call as a vertically stacked network device, right? So it has the control program, which is figuring out how to do forwarding, and then the data plane part, which is actually making the decisions or actually transforming the packets and forwarding the packets, right? So there's a one vertical vertical stack, which is all integrated into one device, right? What software-defined networking is saying that we will do a logical separation between the control plane and data plane, right? So the devices that are out there, they should be dumb, and they should only do forwarding. And the software or the control part that is making decisions, that should be the smart piece, and it should not be sitting on those devices. It should be sitting somewhere else. So we have to logically separate them, and then it sits somewhere else logically and makes decisions, and then sends those decisions to the devices, right? So that's a logical separation that software-defined networking talks about. So when we talk about software-defined networking, we have control programs, right? So these are programs that are deciding how the network should behave. And these control programs, rather than operating or rather than worrying about how exactly the physical network looks like, it works on a global view of the network, right? So it is basically working on some abstracted graph that are representing the network underlying it. But these are very simplified abstracted graphs that's abstracted from the network. And then these control programs operate on that graph and say like, okay, to go from point A to point B, this is the route or this is the path that a particular packet should take. And then it conveys that message to the devices, and then forwarding entries are updated, right? So global network view of the network is important for software-defined networking. And then there's also a notion of network operating system, right? So these control programs don't have to directly interface or interact with the hardware devices, right? So there is a network operating system. The operating system treats these network devices as basically, peripheral devices. It has its drivers, or you can think of an API for interacting with these devices. Those are called southbound API because that's the the south part of the interaction. And then there are these northbound APIs that are for the control programs or the software programs interacting with the network operating system, right? So open interface to packet forwarding, southbound APIs, and then it has at least one network operating system, maybe more, right? And we'll learn in future lectures that why do we need more? Why is one not enough? Or what are the pros and cons of having just one network operating system versus a distributed set of network operating systems? But I think as I was mentioning that some key attributes is that logical separation of control plane and data plane, presence of a network operating system which has clear open interface to packet forwarding, and then this network operating system, which is in most cases the desired approach is to have an open source version of the operating system, right? So this is kind of like a high level and overview of what software defined networking key requirements are and how is it different from the traditional view of the network. As I was mentioning that network operating system is something which is integral part of software defined networking. The network operating system is a distributed system that creates a consistent and up-to-date view of the network, right? So what does that mean? I was mentioning earlier, right? So that the control programs, they don't want to know exactly what type of device it is, what type of capabilities it has and all those things, right? So all that detail has to be abstracted away. And the control program is just working on some graphical representation of this network, right? And the view of the network can change. Maybe some links can go down, and when that happens, then this graph that is exposed to the control programs that has to change, right? So that is what I meant when I say, like, the graph has to be consistent. It has to be up-to-date representation of what the network is right now, right? And it should run on servers. So, like all controllers in the network. And there are good examples are Nox, Onyx, Trema, Beacon, Mastro, and ONOS that we will be covering. But something to mention here is that I mentioned it explicitly that it has to run on servers, right? And that's where I'm saying, like, this, like the previous generation of networking devices were vertically stacked, and which means that the data plane and control plane was sitting on the same device. Now, what happens is that, like packet forwarding and control programs, they have very different computing requirements, right? So one will require a lot of CPU cores to decide and apply an algorithm and figure out, okay, what decisions need to be made. And the other is the one that is handling a lot of packets coming at a very high speed. And then it really needs to make very, very fast decisions such that it doesn't become a bottleneck and just pushes the packet out, right? So these are two different compute requirements that we have from one device, right? So this vertical integration that we had in the previous generation meant that we were trying to satisfy two different computing requirements from one device. And it meant that it has to, like, those devices ended up being very expensive because they were solving two different problems. And that was one reason why these devices were very, 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 very expensive. A very high-end device capable of handling maybe hundreds of Gbps of traffic and supporting state-of-the-art protocols like BGP, Ospf, and all those things. We were talking about few $100,000, sometimes $1 million for one device, right? And that is very expensive. And just to put things into perspective, a switch or a device that can handle 3.2 terabits per second worth of traffic now costs around $6,000 or maybe $8,000, right? So that's a huge difference compared to where we were and where we are now. And that is because we have this logical separation, right? And we'll learn more about like what enabled it, how it is helpful, and all those things. But this separation of control logic, like pushing away this control code from these devices to some logically centralized location, and like keeping the switches dumb such that they only focus on enabling forwarding, packet forwarding, right? This is a huge game changer in terms of cost. And that is one reason why companies like Google and Microsoft and others have been able to thrive, even though they are carrying so much of traffic on their network at their data centers. Like, it's orders of magnitude more traffic that they're handling now, but it is also orders of magnitude less cost that they're doing it with. And that is the only reason why these companies have been very successful, because they were able to bring down the cost and make more profit, right? So software-defined networking played a huge role in enabling these companies to scale up, right? And we'll learn more about how exactly that happened, what are the fundamental principles. But I just wanted to share this perspective with you that, how critical role a software-defined networking and how important it was to do this separation between the control plane and data plane, and how it was a big game changer. And getting back to this concept about network operating system. Network operating system uses forwarding abstraction, right? So there is something called forwarding abstraction, where it gets the state information from the forwarding element. So when I say forwarding elements, think about network devices, right? So the forwarding abstraction that is supported by network operating system is doing two very simple tasks. One is to pull some information from these devices such that it can create a more consistent state of the network, right? What is network state? Which links are up, which links are down? How much capacity is available in each of those links and all those things, right? So it's basically polling these devices, figure out what is the current state, and then the control program uses this information, applies all the state-of-the-art algorithms to figure out, okay, like now, how should I reconfigure or configure this network such that it can operate in a much optimal manner, right? So then, those information, those control directives are sent down again to these forwarding elements to enable packet forwarding, right? So this is kind of like the basic job of network operating system, that it is supporting these applications or control programs, and it is interfacing with these devices, providing a good like open vendor agnostic interface such that an operating system can interact with devices coming from multiple vendors like Cisco, Juniper, or Arista or somebody else, doesn't matter which vendor it is coming from, the network operating system is able to interface with all of them and then understand the current state of the network, let the control programs make decisions, and then it enforces those decisions in the network. So talking about control program, as I mentioned, has been operates on view of the network. It takes as input the global network view. You can think of that as a graph. You can think of that as a database that is being updated by the network operating system. And then the output is the configuration for each network device, right? So it basically decides that, okay, what should be the entries, forwarding entries on device 1, forwarding entries on device 2, device 3, the entire network, right? So this all happens, or these decisions are made by the control programs. And the only input that they need is a network view, which can be represented as a graph or a database, which is the most updated state of the network. Now, control program, it is important to mention here, is not a distributed system, right? Because it has a centralized view of the network, right? So it is the network operating system is pulling all these devices, creating a database, creating a graph, which is a centralized view of the network. So that simplifies how we write these programs, right? As I don't know how many of you have taken distributed systems classes, but as you can imagine, to writing a software program that operates for distributed systems versus the one that operates on a centralized system, it's a totally different ballgame, right? So writing a program for something that is logically centralized is very, very easy logically. You don't have to worry about consistency issues. You don't have to worry about communication overheads and all those things. Pretty simple, right? And this abstraction is hiding away all the details there, and then it just provides a centralized view. So control program gets much easier to write. And elaborating a bit more on the forwarding abstraction. So the purpose of forwarding abstraction is to abstract away the forwarding hardware, right? As I mentioned, there can be different vendors who might be making these hardware devices. We don't want to write a network operating system or a control program that has to worry about what type of device we are going to use, right? So it has to be agnostic to what vendors we are using. So, to abstract away that forwarding hardware, we have to provide this forwarding abstraction. And of course, it offers flexibility because the behavior is specified by the control plane, and it is built from basic set of forwarding primitives, right? So forwarding primitives, you can think about primitives such as drop the packet, or forward to a particular port, or maybe recirculate the packet, clone the packet. So these are the primitives that I'm talking about, and these are kind of like the ones that are used in the forwarding abstraction to make decisions. It is of course minimal. It is streamlined for speed and low power. And the control programs, as you can given this vendor agnostic approach, the control programs are vendor agnostic as well. And I want to mention here that OpenFlow is an example of such an abstraction, right? So sometimes, especially in the earlier years of software-defined networking, OpenFlow and software-defined networking were used in the same sense, right? But they're very different things. So software-defined networking is a principle, and among many things, it has something called forwarding abstraction, right? And OpenFlow is just an instantiation of that forwarding abstraction. OpenFlow is not software-defined networking. It is an instantiation of one type of abstraction that is fundamental to SDN, right? So SDN is much bigger than OpenFlow. OpenFlow is just an instantiation. SDN is a principle, is a concept which has multiple abstractions. Forwarding abstraction is one of them, and OpenFlow is an instantiation of that. So this distinction is important because when you go out and people are like, okay, SDN, OpenFlow, same thing. It's not, and it's a subtle argument. It's a subtle concept, and we'll learn more about OpenFlow as we move forward. But I just want to point out that this is where a lot of people used to get confused about SDN, about OpenFlow. So we have to understand that OpenFlow is just an instantiation of forwarding abstraction, but there can be more forwarding or different types of forwarding abstraction, and that can still be called SDN, right? So any questions so far? Okay. So let me give you a quick overview of software stack for SDN, which is like more inspired from what is the state of the art right now. And if you don't understand each and every term that I'm using here, it's okay. You're not required to. But during the course of this quarter, we will learn everything that we are going to talk about in the software stack. And as part of your assignment 3, we'll actually be able to write a SDN app or control app using all these different components that we're talking about in the slide, right? So, like the top, we are going to unravel this software stack top down. At the first layer, we have these control applications, right? So they're I've been repeating myself so long that there is this network view that is abstracting away all the details that is offered to the control app, and then control app uses that centralized network view, writes its logic about what the network should do, right? Then there are these APIs that it leverages to interface with the network operating system, right? So basically, the APIs are basically how is the network operating system exposing the network graph to these control apps, right? So that you can think of that as an API or as part of the API here. And ONOS, as I've been mentioning, is one example of network operating system. And then, as I mentioned a while back, that because this is the interfacing between the control app and network operating system. So if you look at this as a vertical stack, this is called the northbound interfaces, right? So how is the control app interacting with network operating system? Those APIs are called northbound APIs. And then we have the southbound APIs where the network operating system interacts with the downstream device, right? And so far, I was calling these downstream devices as a forwarding element or network device, but then it is richer than just being a silicon, right? So of course, the base of it will be a merchant silicon, just a silicon. You can think of an ASIC, integrated circuit, which is application specific. ASIC is something which is heavily used for networking, though FPGA is also used, but let's focus on ASIC right now. It's very specialized. It does a specialized set of tasks. And then to do a low-level programming of that ASIC, we have a switch OS, switch operating system, right? Like a simple ASIC cannot handle the messages coming from the network operating system, right? So there is a small operating system that is sitting at the switch, and it is interfacing with the network operating system. It is, it is very low level, extracts all the information, or executes all this insights into the network. And this is called southbound API. The interface or the interface between the operating system and the switch or the hardware target, it is called the southbound. And what is an example of a switch OS? So Stratum or ONL is a good example of a switch OS. And what is an example of a merchant silicon? So Tofino, Tofino is one instantiation of a merchant silicon that is used as a forwarding element in software-defined networking. Tomahawk is also from Broadcom. What is interesting and noteworthy here is that Barefoot is one of the company that started as a startup coming out of Stanford, and it came from the same set of people who started OpenFlow, and then they started a company called Nicira, which got acquired by VMware for a couple of $1 billion. And then they started this company called Barefoot, where the fundamental question was, okay, can we design a merchant silicon that can be reconfigured on demand, right? And that's kind of like a very onerous task, and we'll learn how that was all enabled. But that was, I would say, a bit of a game changer in this space, because that provided a lot of flexibility, enabled a lot of use cases. And recently, when I say recently, maybe a year and a half ago, it got acquired by Intel. I don't know for how much, but it must be significant. And now this Barefoot or Tofino is part of Intel Tofino. And we have hardware switches that we have bought as part of our research. So what we will be working with in this course will be more with the software versions or software emulations of these switches. But the level of detail that we will be getting into will prepare you to even write programs for these hardware switches, right? So if you're interested and curious, you can, like work with me and write those hardware programs, work with our lab here. But, like if not, then what will you be prepared for is to write software that can control these software emulations of these hardware switches. And that will give you a good exposure about how these things work in real world, right? So it's okay if you don't understand all these nuances here, but as long as you understand the high level concept, that should, like, this is a good window into type of concepts and, ideas that you'll get exposed to as part of this course. Will be, like exposing you to ONOS, will be exposing you to these interfaces, like, the runtime interfaces, and the like subtle details about the operating system also for the switch OS. Like not too much for the switch OS, but a lot more focus will be on the ONOS stuff. All right, and finally, I think, we're talking about the P4 language. So, like what you can do as part of P4 is that you can write a program with, .p4, switch.p4, forward.p4, and then that compiler will actually reconfigure or configure this merchant silicon for you, and then it will do a specific task, which is, like very specialized, tailor-made for the program that you want to enable in the network. And this might all sound a bit vague and abstract right now. As we get into the details of it, we'll understand. But like the biggest takeaway here is that the previous generation of hardware switches, they were custom designed for a specific protocol, right? So you have learned about BGP, you have learned about IGP, OSPF, or whatever. So if you go out in the market and say like, I just want a switch which can do a very simple OSPF version of OSPF, right? You probably will be, shooed away from the vendors. So like, no, we don't sell those type of devices. If you want, you have to buy this expensive one, which can do BGP, OSPF, whatever, right? And like more protocols that support the hardware cost just goes up. So that was kind of like, if I don't need XYZ protocols, why should I pay for it, right? That was kind of like the mindset people were coming in. And then, this barefoot stuff came in and they were like, okay, we can design these custom packet processing pipelines where you can enable whatever protocol you want, right? So it is independent of protocols. Like, it is not necessarily designed to support BGP, OSPF from get-go. If you want to support BGP, you write a P4 program that will support packet processing for BGP or support this BGP protocol, right? So it's very powerful because that took away the need to do all this protocol design in the hardware to software, right? And that can be very empowering because then if I need these devices for very, very simple tasks, I don't need to pay that much of money, right? I can just buy these silicon and write a very simple switch program and configure that pipeline that does that very specific task and nothing else, right? And that just brings down the cost significantly. So like this is a motivation why people were focusing so much heavily on these protocol independent architectures. And we'll learn about what those protocol independent switch architectures are and how can we write a program that can configure a packet processing pipeline for hardware switches, right? So that's something that you will be learning as part of this course. And like so far, I think like I've built some motivation for you, like why software-defined networking, but I'll try to connect it more with the motivation for these different industries and specifically focusing a bit more on the use cases of software-defined networking. So I think like I mentioned before as well, that there was this vertical integration that was going on in these hardware devices, right? So you think of companies like Cisco, Juniper, they were selling these hundreds of $1,000s worth of devices where there was a specialized hardware and a general purpose operating system all integrated into one. And, basically these devices were sitting as one unit. And then, like to enable any type of routing, they had to support a particular type of protocol like OSPF. And if I'm sure you learned about OSPF, which is basically trying to find the shortest routing path using the Dijkstra algorithm. And basically these blocks are showing that how much of the resources were consumed by that specialized hardware that was taking care of packet forwarding, how much of resources were there for the general operating system part, and how much of resources was spent with the OSPF, right? And that's significant. There was an RFC which enables OSPF in these devices that was worth 245 pages. and it spent a lot of time on how do you create this consistent up-to-date map of the network, right? Because these are individual devices, they have to send some messages to their neighbors, the neighbors have to send some other messages, and then eventually some other messages come back to you, and that gives you a consistent state of the network. And then once we have that consistent state of the network, the Dijkstra algorithm is just one page worth of information, right? All the other information, all the other resources and energy spent on figuring out this distributed state or consistent state in the distributed settings, right? So if I go with the approach that software-defined networking, which is logical separation of control planes and control plane and data plane, and logically centralized control plane, right? So then what I really need to do is that basically have this Ospf Dijkstra, which is just one page worth of algorithm written into the control program, and then I'm done with that problem, right? So as I was mentioning that that creating that network map was using 95% of resources, and only 5% of resources were spent on Dijkstra. So if I go with the software-defined networking route, which is logically separate the control plane, data plane, make this control program work on a global network map, right? Then Dijkstra is a very simple algorithm to apply, and then it can significantly bring down the cost of running that algorithm, right? And what it really means is that these abstractions enable simplicity. That simplicity enables these devices or these networks to scale, and which brings down the cost, which is very, very critical for every company out there, right? So this is kind of like a high-level motivation, like a bit more concrete example of where the resources were getting wasted in the previous generation of networks, and then how software-defined networking is enabling it to address that problem. Moving on, I think there were a bunch of killer use cases that came out around that time, which basically forced the networking community out of the previous status quo, right? So I think even though in hindsight it looks like it was such a natural thing to do, and I'm sure there were researchers who argued that things should be done this way, but unless there is a resonance between what can be done and a motivation to do that, a lot of ideas just die out, right? So this was the perfect resonance between a new set of ideas coming out and a vacuum of a significant need or pull for these type of ideas, right? That happened, right ideas came out at the right time, is one reason why SDN became such a mainstream thing, right? So one such an application was related to virtualization, right? So when we talk about these companies like Google and Microsoft and Amazon, so they had the virtualization sorted out for for these compute devices. So rather than connecting a program to a single hardware, they basically are focusing, or they came up with these ideas about virtualization in the hardware, and they were focusing more on virtual machines rather than physical machines. But then these virtual machines have to be connected with each other, right? And technically, I don't want to, when I'm writing these type of distributed programs, I don't really want to worry about the network part, right? So think about this figure that we have. I'm showing you 4 VMs here, 2 VMs here, 2 VMs there. And if I want to provide an abstraction where all these virtual machines are part of just one local area network LAN, right? If this is an abstraction which will make a lot of sense, because when I'm writing this program, I don't really want to worry about how this packet from virtual machine 1 will go to virtual machine 3 or 4, right? I don't want to worry about that. So that is what virtualization brings in, that it provides an abstraction, simplifies, okay, let's provide a logical view of the network. Let's not worry about the physical network. Let's provide a logical network. And in that logical network, all these virtual machines are connected with each other directly, right? So you just say forward to virtual machine 4, it should go there, right? And you don't have to worry about all the configuration changes that you have to make in the network to make that work, right? So this is just a simplified version or explanation of virtualization, but virtualization was very, very powerful, right? Think about these like Google Photos or Facebook type of applications, where virtualization or virtual machines are critical for those distributed programs that are supporting all these applications. And all of them cannot be physically present on one hardware compute resource or even a rack of servers, right? So you will need maybe hundreds of rack of servers, or maybe thousands of rack of servers, and all those thousands cannot be physically located in one location, right? So they have to network with each other. They have to provide that simplified abstraction. So that is the motivation for virtualization, that like, let's take away the networking part from this problem, right? Like, let's not worry about network. Let's provide an abstraction where all these virtual machines can be directly connected with each other as a one-hop network, and the underlying network should be reconfigured such that it can enable it, right? So when a packet leaves from this virtual machine, it goes through a virtual switch, then it goes to a NIC, then a bunch of switches, then another NIC, another virtual switch to that VM, right? So this is the path that packet has to traverse. But as a programmer, when I'm writing these programs, like Facebook, the content delivery programs like Facebook, Netflix apps, and all those things, I should not, as a developer, I should not worry about these things, right? So that is a basic principle of virtualization. And with software-defined networking, as we will learn, it was a very easy thing to do. So this was kind of like one of the easiest and one of the most motivating, clear motivation that was driving software-defined networking. And as I mentioned earlier, a company called Nicira. So, Nicira was a startup that was based on some of these initial ideas around software-defined networking, and it was providing exactly this service, right? So two virtual machines on completely two different networks should have an abstraction that they're directly connected to each other. How do you enable that? All that magic, all that detail should be abstracted away. And that was basically part of Nicira's product. And it got acquired for 1.4 or 1.2 billion. I don't know the exact number. And this is around 10 years ago, right? So you can imagine how big that number was back then. But it's just a strong, powerful idea. But that also drove, that provided a lot of momentum for software-defined networking, because things started to look very real as it moved forward. The other application is related to traffic engineering. So in 176A, you probably learned something about MPLS, and you learned about Ospf. So Ospf I've been referring because Ospf is a very common protocol used, but it's a distributed protocol, right? So when a flow, like flow A wants to go from point 1 to point 2, it will basically try to figure out what is the best routing path. And in this case, it had two hop paths to go to that destination, right? But it chose one of them because it's equal cost. So it can be a random decision, and it's kind of like, okay, path 1, path 2, same cost. I'll just pick path 1, right? So in this case, A picked that. But now there is a new flow, which is B. And because A is already using that link, so B will go through this fifth switch, and it will, this is still fine, right? Like there's no overlap, no underutilization of capabilities. But now when a third flow comes in, which wants to reach the same destination, but now it sees that, oh, all these links are heavily utilized, and there is no easy way for me to reach there. So maybe I'll take a bit of a circuitous route, which is less busy compared to the others, but still, I'm still sharing that link with A. I'm still sharing that link with, or still sharing some links with B, some links with A. So I'm still, not going to get a free or leverage the full capacity or full capabilities of this network, right? So it's a bit of a suboptimal, because each of these devices are making individual decisions about routing, right? So it's a distributed decision and leads to a suboptimal routing. But now, if I have a logical view or centralized view of the network, I would actually come up with a different routing path. I would say, A should go this way, B should have a direct link here, and C should have a direct link here. All of them are non-overlapping, and they will be, leveraging the full capacity of the network out there, right? So this is optimal routing. This is only possible but I have the full view of the network, right? I'm not operating on a partial view of the network as most of the distributed protocols are. I'm operating on the full view of the network, and that enables me to have this type of optimal routing. So this is a very toyish example for what traffic engineering really is, but this is very fundamental to how most of the modern wide area networks are designed, right? So somebody mentioned Google. So around 2013, Google and Microsoft both came with two different research papers talking about similar idea, similar concept about how they enabled software-defined wide area network in their settings, right? So Google's was called B4, and Microsoft's was called SWAN. And both of them had the same set of principles, and they were literally addressing the exact same problem that I'm showing you here, that if I go with the top version out here, then I have to over provision my network, right? So if I want 100 Gbps capability, I have to provision my network for 200 Gbps such that I can support it, right? Because C and A and C and B are sharing the links with each other, right? So if I want 100 Gbps capability for C, then I have to make sure that the link between link which is shared by B and C and link which is shared by A and C have to be 200 Gbps, right? So in general, my, like I'm over provisioning my network, right? And if I'm using the solution like the centralized view, then I only need 100 Gbps network, right, to support 100 Gbps workload. So A, B, C, 100 Gbps. I need all these links. As long as these links are all 100 Gbps, I can support that type of workload requirements, right? So this is kind of like a fundamental difference. This is how it made a huge difference in the cost. In this course, we will get a bit more into the details of this problem, understand what are the other nuanced challenges around enabling this type of traffic engineering solution, how Google addressed it, how Microsoft addressed it, get exposed to all those ideas as well, right? So just want to give you a taste of what we are going to cover as part of this course. And of course, then there is a motivation for network telemetry. This, I would say, was a bit of an afterthought. I don't think a lot of these SDN researchers started with telemetry as the first order goal, and but they kind of like the primitives or the abstraction that they were providing. It was very easy for them to support this abstraction where you can instruct these hardware devices to not only make simple forwarding decisions or apply these forwarding rules. You can also apply a rule or an entry which specifies that, okay, what type of information should be collected from the network, right? So consider the setup. A packet with a header and payload comes into a switch. I can write a program which says like, add the identification or ID of the switch at the time when this packet arrived at the switch, at the time when it left, also add the time it took for the packet to clear the queue, right? So when it got enqueued and when it got dequeued, what was the time it took, right? So all this information can be very, very useful for me from diagnostic purposes, right? So if I want to understand that, okay, is there any link in the network where the queue, like the waiting time for a packet is very high, right? So if I have this information stored in some database, I can just run a query and say, like, oh yeah, like switch one is having a high queue, and then that information can help me make better decisions. Maybe I'm sending too many packets. Maybe I'm using some suboptimal routing paths. So that that is information is power here, right? So but like the conventional devices, they were not really tuned for extracting this type of information from the network. And why, we'll learn later, right? So in this course, we'll learn like why that was such a huge issue and problem for the existing networks, why it is so easy for the SDN based devices, and what type of use cases it enables, right? So I'm like, in this case, I add all this information as a metadata from switch 1. Then it goes to switch 2. I add this information as metadata from switch 2. And then when it goes to switch 5, then I also write a program that not only add this metadata, but also, report this metadata to some other server, right? So all this metadata is carried with the packet. Then the program at switch 5, what it does is that it extracts it out and send to a different port, which is connected to the monitoring server. And then monitoring server looks at all this metadata, dumps it into a database. You can create a visualization, dashboard out of it, or you can, write some other control programs. And this is an exciting use case because you have one of your programming assignment that is going to do something similar, right? So, I feel very excited because this was very empowering from networking researchers, network operators perspective that, hey, rather than relying on really, really old arcane tools, which are good for nothing, now we have this network where we can actually program and say like, okay, what type of information we want to extract, where do we want to extract it from, what level of details we want, and we can, once we have all this data, then we can, write all these cool visualization or analysis tools, right? One catch in this whole setup is scalability, right? So when we're talking about 100 Gbps links or TBPS worth of traffic, we're talking about billions and billions of packets, right? So if I write very naive programs that, hey, collect all this information from every packet, we're setting ourselves up for a huge scalability challenge, right? So that's something that is very important and exciting. And that's something which is also related to or connected to how SDN, the future of SDN will look like, right? So we will discuss all those details and nuances as we proceed in this class. But I think, This is just a snapshot for you to understand that, hey, there is this application that is coming out of SDN. It's very powerful because it gives you the full descriptive view of the network, and then you can make some really interesting control decisions based on that. All right, so I think now we are getting close to the end of this class. I want you to have the takeaway that this course focuses on learning the fundamental principles that are guiding designs of these software-defined networking, how these principles have been applied in terms of applications, what those applications are, how exactly they have been used by companies like Google, Facebook. I don't like naming their names, but I think those are success stories of how these principles and ideas developed in academia were influential in solving and addressing fundamental problems in the real world, right? And then we also talk about the related future work, especially when what I want to cover is that how software-defined networking can enable a future where networks can run on their own, right? So those are called self-driving networks, and how all this flexibility that is offered by software-defined networking, both in terms of collecting information and controlling or executing this control programs in the network, how it enables networks to make decisions on their own and not have any human operator manage them, right? So that's kind of like the ideal future. We're not there, but we can be there, right? And that's something that I will cover as part of this course as well. What building blocks that SDN provides that will be fundamental for us to enable the goal of self-driving networks. And more importantly, I think you will get some hands-on experience working with software-defined network software stack. We'll be working on different portions of the stack, but most importantly, we'll be focusing on the hardware targets. We'll use the P4 language to program a hardware target. We'll focus on a couple of assignments based on that, and then we'll be writing a general application, SDN application within a state-of-the-art ONOS controller. All right, so so I guess this brings us to the end of this lecture. But you can ask me a lot more questions, and I see there are already 2 questions out there. So one question is about how does SDN correspond to the 5 layers: application, transport, network, data, physical of the network? And the other question is, does the reading go over what we talk about in the lecture as well? Yes. So the reading, I'll answer that easy question first, which is that the reading that I have listed on the course website is very relevant to whatever topics we are going to cover in the class, right? So if things that I'm teaching are not super clear, reading things in those references that I have pointed out will make it easier. But I want to make sure that you understand that reading those references is not a requirement, right? You should be able to answer questions in the quiz, but for your your own knowledge, I'm providing you all the references such that if you're curious, you can go and read those references and develop a much deeper understanding of these topics, right? Okay, so the other question is about how, where does SDN fits into these layers, right? So we have to understand that, these layers are, part of the packets, basically, there are different levels of controls, right? So layer, application layer, all the way to transport layer, these are all end-to-end control things, and then we have the network layer, right? So typically, software-defined networking falls into the category of network layer, right? So it is basically, changing fields, or it is capable of changing fields in the network's network layer, right? So IP layer or IP part, but that is kind of like a very basic answer, but technically, you have access to all packets header, right? So you can change fields that are beyond just layer 3 header fields, right? So layer 3 are IP related header fields. You can maybe also change some layer 4 fields, but that will disrupt the end-to-end connectivity, right? So I would say that we can view software-defined networking or these programmable networks from 2 perspectives. One is to read the information in the network. From that perspective, you can read information about any layer, right? And the second is to make some changes to the network layer. So there you should only, not to the packet, but there you should only change things that are, network related, right? So the network layer, IP layer decisions, I can change the destination IP without making any type of disruptions. I can change the ports and others without making any significant disruptions. But other than that, I think that's where I would see software-defined networking to play a role. Application layer, I do have packet in the fly. I can make some changes, but that's that's going to be a bit more disruptive, right? I hope that answered the question that you were looking for, but we can always chat offline if you want more details. Other questions before we leave?
I have a question. So at least in this lecture, you talked about a lot of things or like vocabulary or terms or like abbreviations that we've never really talked about in 176A. And I just took 176A, so it's still, things are pretty fresh and I've never, so I was wondering if like all the things you've talked about today are things that you're going to talk about a lot more later on, or?
Yes. So I think like it's a good question as well as good feedback that there are these specific terms that we will be covering and will be referring. So yes, we will be covering each of them in more detail, and you'll have a very good understanding of each of those terms as we proceed. But what I will also do is to like maybe give you all a list of these abbreviated terms that will make it easier for you to grasp, right? So we can be more explicit about what these each acronyms and terms refer to. And you should feel free to point out if anything is completely unclear, right? So if there is any term that is still like even with all the discussion that we go as we move forward, it's not clear, just ask, right? And I'll be more than happy to clarify any of it.
All right, thank you.
All right, what else? All right, I think I'll let you folks soak it in. This was probably like a more intense lecture, and I hope that gave you a good sense of what this class is going to be about. But if you have any questions, just feel free to reach out to me over Slack. I'll be more than happy to answer any of your questions. Before I leave, I also want to make a remark here that these are difficult times because we don't know whether there will be in-person classes after 2 weeks or not, or like what will be the overall structure. Like there are some moving parts here. Like you're more than welcome to come to the office hours and have more in-person interactions with me. I'll be holding both virtual, physical, whatever is according to university's guidelines, offices. But I will highly encourage each of you to at least schedule one meeting for the office hours, right? Because I think it's like during these remote lectures, it's really hard to make connections and understand what your understanding of the course is so far, what is exciting you, what is not exciting you. I think it just makes it easy, especially if we are not having in-person lectures in the future. It will be like, I'll highly recommend that you at least schedule one meeting over the office hours. Like I'll send out a spreadsheet for you folks to sign up for the office hours, but like during the office hours you can always just jump in, and I'll be more than happy to talk anything about the topics here. All right, before we leave, I think like this is kind of almost time, so any questions before we leave? Are we all good? Okay, I'll pause the recording now.